In the last video, we introduced rate laws, and now we can actually put this to practice and write out an actual rate law for a particular reaction without x and y as the order. We can actually experimentally determine the order. So here we have 2N2O5 giving us 4NO2 plus O2. Okay, when we write a generic rate law, first we want to write the rate is equal to K times the concentration of the reactants to a certain power. And in this case, we're going to say to the x power. We're also given some experimental data here. And we can look and see we have two data points, and this should be enough to figure out what this rate law expression will be. Okay, we know that the rate here is going to equal 5.4 times 10 to the minus 4 molar per second. Okay, and that's going to equal the concentration of N2O5 to the x power. Okay, here we have two data points, right? The first and the second. So we can kind of set up a proportion to figure out how this change in concentration is going to influence the rate. So we kind of set up a proportion where, actually I forgot the rate constant K here, right? Where the rate is going to be K times the concentration of N2O5. So for data point number 1, our concentration is 0.9. That's to the x power. That's going to equal 5.4 times 10 to the minus 4 molar per second. If we set up a proportion with our second data point, we have K times the concentration of N2O5, which is 0.45 molar, also to the x power, is going to be 2.7 times 10 to the minus 4 molar per second. Because the reason we set up this proportion is because we need to see how the concentration of N2O5 is changing with the rate. Okay, so we can kind of simplify this expression a little bit. Okay, the constants are going to cancel here, and we can rewrite the left side of this equality here to be 0.9 divided by 0.45 to the x power is going to be equal to 5.4 times 10 to the minus 4 molar per second divided by 2.7 times 10 to the minus 4 molar per second. Okay, and remember, if you remember back from algebra, this is one of the laws of exponents, where if you have two exponents divided by each other, you can manipulate that expression to take the two things, in this case the two concentrations, inside the parentheses to the x power. Okay, so if we do this, so we do 0.9 divided by 0.45, that's going to be 2 to the x power, okay, is going to equal 2. All right, and just by inspection here, we know that x would be equal to 1, but some of the times it's not going to be quite that easy. So what we can do is, if we take the natural log of both sides here, when we do that, we can take this exponent right here and put it down front. So we can say that x times the ln of 2 is going to equal the ln of 2. And from this, x is going to equal 1, which tells us that we have a first order reaction. Okay, and from that we can write the rate law as the rate is equal to K times the concentration of N2O5 to the first power. Okay, so this would be our particular rate expression. We can now calculate what K is if we know what the order is. Okay, so if we look back up here, and we can either take the first data point or the second data point for this, because we know that the rate is going to be equal to 5.4 times 10 to the minus 4 molar per second, which is going to equal 0.9 to the first power. Okay, so that means sorry, it would be k times 0.9 to the first power. So that means when we go to calculate this, we can calculate k, and k is going to be equal to 5.4 times 10 to the minus 4 molar per second divided by our concentration, which is 0.9 molar. So here the molar units cancel out, and our k is going to be equal to 6.0 times 10 to the minus 4 seconds to the minus 1. So our overall rate law then, if we can combine this k term with the rate law that we have down here at the bottom of the page to say that the rate is going to equal 6.0 times 10 to the minus 4 seconds to the minus 1 times the concentration of N2O5 to the first power. And this is our rate law for our particular reaction given the experimental data that we have right up here. Okay? One thing that I want you to note here is that when we go from data point 1 to data point 2, okay, we're cutting the concentration in half. Okay? So the question we need to ask ourselves is, what happens to the rate when we cut the concentration in half? And if we look here, we go from 5.4 times 10 to the minus 4 to 2.7 times 10 to the minus 4. We also cut the rate in half. So by decreasing the concentration by a factor of a half, we also decrease the rate by a factor of a half. Since these two right here are equal, we can say that we have a first order rate expression. All right, so the exponent here, and we'll go into some examples with some more difficult expressions, but here we're looking in the rate law. We want to know what happens if I cut the concentration in half. Or if we go the other way over here, when we go from 2 to 1, we're doubling the concentration. So what happens when we go from 2 to 1 here? We also double the rate. So if the concentration and the rate both double, then we have a first order reaction. Okay? And we'll look into a couple more examples of this and go over some more details in the next video.